Hello, Chemistry 130L. This week we're going to be looking at water to try to understand some of the bonding and properties that happen with water. Now, back in Chem 100, you probably studied water extensively, right? We know water as this molecule right here, H2O. It's a small, very polar molecule with strong intermolecular forces. Now, why does it have such strong intermolecular forces? Well, water can, if you recall, can hydrogen bond. Okay, we have these two hydrogens right here that are attached to the oxygen, so both of those are capable of hydrogen bonding. And then on our oxygen, we have two lone pairs. So that oxygen is capable of accepting two hydrogen bonds. So water is unique in that it can undergo 4 simultaneous hydrogen bonds all at one time, which is part of what gives water its unique properties. It's why it has such a high boiling point. It's why it has such a high heat capacity. So we're going to look at water. We're going to look at some solubility, some adhesion, cohesion, some heat capacity, some various different properties of water within this experiment. Now, to compare, we're going to also look at isopropyl alcohol, okay? Which you can draw out the whole structure like this, or we can use our easy carbon framework structure and draw it out like this. Now, isopropyl, okay, it is polar like water is, but instead of just having oxygen and hydrogen, now we have a 3 hydrocarbon chain that our hydroxyl branches off of, okay? And so when we look at it, can we do some hydrogen bonding? Yes, because we have a hydrogen right here. So this hydrogen bond is capable, this hydrogen is capable of participating in a hydrogen bond. The rest of these hydrogens are not because they're bonded to carbon. So we have a little bit different intermolecular forces going on there because not only are we going to get some hydrogen bonding from this hydrogen, but we also are going to get more dispersion forces from our hydrocarbon side chain than we would just from our water right there, okay? So we're going to use those as a comparison. So before we get started, we need our protocol and we need to figure out all of our supplies. This experiment actually is going to require quite a bit of outside supplies. All right, so first off, we're going to get our Chemistry of Life packet. In that, you're going to find your isopropyl, some benzoic acid, a couple of paper cups, a whole bunch of wood splints, some small little scoops, and then another well plate. All right. And then what you'll need from your general supplies, your 25 ml graduated cylinder, 250 ml beaker, and a couple of pipettes. Okay, and then you're going to need a whole slew of other stuff. So we need a permanent marker because we're going to mark our pipettes, which I've already done. Okay, I've got some table sugar, table salt, finely ground black pepper. I have a lighter. I have tap water. I have my phone, which is a good stopwatch or timer device. Okay, I've got some dish soap. And then in my kitchen, if I were to do the part where I light stuff on fire, that's where I would have access to the running water and I would have my fire extinguisher. Okay, or not even just in my kitchen, but in my little attached laundry room over here. All right, before we get started, it is important to make sure that we have our PPE on. So I'm going to go ahead and get my PPE situated. Okay, so I'm going to fasten up my lab coat. Going to put my goggles on. Going to put my gloves on. Okay. All right. Okay, for our preparation, once we have everything, it wants us to put the tap water in our beaker. So if I was in the kitchen or in my room, I could just put the tap water directly from the tap into the beaker. But because I have to prep everything to bring out here, I have the little bottle I pour from. So there I've got my tap water. Okay, and then I have labeled water and isopropanol on my pipettes. Okay, all right, so our well plate. Remember that we've got A, B, C, D going down the side and 1 through 6 going across the top. And that is how we are going to figure out where to put stuff. So I've oriented my well plate so that my A1 is up in the corner here. And now I'm going to transfer 2 mils of isopropanol into my A1, A2, and A3 wells. So I'm going to use the correct pipette. Now, the isopropanol in my kit is labeled 2-propanol. Okay, it's 2-propanol because we've got a propane, and then we've got the hydroxyl coming off of carbon 2. So that's where we get 2-propanol from. The OL, that's the ending for the alcohol that has a hydroxyl group. And then again, propane, our 3-carbon chain. Okay, so in wells A1, A2, and A3, I'm going to do 2 mils. Okay, so with the pipette, remember that approximately 20 drops is a mil. So I'm going to drop 40 mils. Okay. Okay, and then my water pipette. Now it's okay that we're using tap water because we're just testing solubility, adhesion, cohesion, and our specific heat capacity. We're not doing an actual reaction where it would matter if there was dissolved stuff in our water. So that's why it's okay that we're using tap water. One thing you can note too is as you're putting it in, you can start paying attention to, is there any difference with how the water goes into the plastic well plates than the alcohol? Okay. All right, so I have my water. Okay, now what we want to do is we want to take our sugar, our sucrose, and we use our little scoops here, and we're going to do 1 level scoop in A1 and B1. 1 level scoop in A1, 1 level scoop in B1. Okay. Put that aside and put the scoop on top of it in case I need it again. Okay, and now we can use our little wooden splints, okay, as stir sticks. Okay, so I could take my wooden splint and I could stir in there to help that dissolve. Okay. All right, then the next thing I want to try is a scoop of sodium chloride. So there's my sodium chloride to A2 and B2. Okay, so a level scoop there. Okay, and a little scoop there. Again, I'm going to put that aside with my scoop on top in case I need it again. And again, I can use a wooden splint to stir. Okay. And then I'm going to notice my solubility. And then now I'm going to do a 3rd scoop. This time, a scoop of benzoic acid in each. A3 and B3. Okay. All right, and then I can use splints again to try and stir around to help it dissolve. I'm just shaking my plate. But it's better to use splints because otherwise stuff can slosh out. Okay? All right. So now, after I've done that, I'll record my observations about the solubility in my observation sections. Did it dissolve? Yes, no. Did it dissolve completely? Did it only dissolve partway? Okay? And I can mark down, what I saw as things were happening. Now we're going to test our adhesion and cohesion. So into our C and D, now we're going to use some more isopropyl. We're going to do 2 mils more in C1, C2, and C3. So what I did is once I got the first 2 mils in, what I'm doing is I'm eyeballing the levels of each one so that they're the same. That way I don't always have to count out my drops. Okay, so there's that. And I'm going to do the same thing with the water. Again, note how the water goes into the plastic well plates as compared to the isopropyl. Okay, there we go. Okay, so now I want to add a pinch of pepper to each of the wells. Okay, pinch. So you'll do 6 pinches of pepper in total. Okay, and notice what happens to it. Does it sink? Does it float? Okay, all right, so I've done my pinches of pepper. Again, does it sink? Does it float? Pay attention to that. Okay, and now we want to see what happens when it coats things. So we're going to dip a splint into well C2, okay? Lift it back up and record observations. And then we're going to dip it back in, record our observations. And then we're going to coat a wooden splint, okay, with some dish soap and dip it into well C3, okay? And then we're going to do the same thing in wells D2 and D3. Now, what you can do to conserve your splints if you need to is I can do my well C2, and then I can coat my other end of my splint with the dish soap and do the other end of that in C3, and then do the same thing for my D2 and D3, okay? Put one end in D2, okay, and then coat the other end in the dish soap and do that in D3, depending on if you need to conserve splints. You should have enough to do a fresh splint for each one, but if you want to conserve your splints for any reason, you can use the opposite ends if you need to, okay? All right, and then your last thing that you're going to do is you want to make sure that the isopropyl is put away because you don't want to catch it on fire. But what you're going to do is add about 50 mils of water to a paper cup. You're going to place it in an empty sink, okay? Then you are going to light your splint, and while holding the water-filled cup, you'll touch the burning splint to the bottom of the cup. So do this in your sink. That way, if there's too much fire for any reason, you can turn the water on right away and dump everything into the water, and it'll put the fire right out, okay? And then the same thing, you're going to also do the end of the cup or like the rim of it, and then let that do its thing, burn down, and record your observations. So again, I'm not going to do that part at all. I'm just going to show you. I would take my lighter and I would light my splint, and then I would do my thing. But because I'm not where the sink is, I don't want to do that part because I don't necessarily want to set my garage on fire by accident. Okay, so that is our experiment today. And the whole point of this experiment is to explore what's going on with water, okay? What's happening between the water and the isopropyl? Why is it the same? Why is it different, okay? I'm not going to tell you what my well plates look like. There's a reason why I didn't bring them up to the screen, because I want you to explore this for yourselves, okay? Is it the same? Is it different? Why would it be the same, or why would it be different? And as you're thinking about these things, think about, again, the structures there, okay? As I mentioned before, water, small, highly polar, can undergo 4 simultaneous hydrogen bonds. Isopropyl, we can do some hydrogen bonding, but we also have significant dispersion forces because that hydroxyl is branched off of that 3-carbon propane there. So think about those differences when you try to analyze what's going on with your particular experiment and what's going on with water. And think about, why is this important, okay? This particular investigation actually came out of the biology division of the Carolina lab kits. So why would this be under biology? Why is water so important that even biologists need to understand water really well? So think about that. Think about why that is such a critical, crucial thing when you're doing your experiment and when you're analyzing it when you're done.